All right, let's make sure that we have the most recent code from the repository. We'll open up a terminal, and I'll change directories into the desktop, and then my folder, and then the ATTC class. Remember to push tab and those will autofill for you. So if we get into here, we can issue an ls command, and that'll tell us you may or may not have some of these labs in yours. To ensure that you have the latest of the repository, you will issue a git space pull command. So the pull should put new stuff in your local folder or directory, and we will be going into the Lab4 folder. In the lab folder, you'll have some of these. There may be additional ones as I've made changes to the repository. The first one that we're going to take a look at is Lab4.1.0. This will be the first code that we'll write against the hardware that we've already connected. You can actually open up Thony right here from the terminal. If I type in Thony and then put space and then I type in the document that I want to open and tab that over, now it will open up the Thony editor. Alright, so let's take a look at what we have in this code. The first line, remember that calls the Python engine, and we're running the new Python 3. And we are importing the library rpi.gpio. And then we import time, but we won't be using it in this program, but we will be using it in future programs. The pin R is the variable name that we are assigning to the R pin of our RGB module, and we put pin R in physical pin number 11. I'm not going to put the green or blue pin in the code yet, just so that we can get to understand how this code works before adding any more complexity. It'll be a lot of duplication of code, so it'll be fairly easy to write the code once we figure out how to get R working. As you recall, when we do something with pulse width modulation, the two things that we need to establish or set are the frequency and the duty cycle. The frequency that we will be setting is pretty high, 2,000 cycles per second. So 2,000 times will the code go up and down within 1 second. So that's pretty quick, and we shouldn't see any flashing of the LED. As far as the duty cycle, we're going to simply just set that at 50% right now. So I've set that to 50. Remember, duty cycle is the on time. Something that's unique about the way that this module is designed differently than the original LED that we pulse width modulated is that the first LED we used pulse width modulation on the power that we created through the pin. So when we went high for the duty cycle, we wanted to turn the LED to high, or the full voltage. And when the duty cycle went too low, the LED went to 0 voltage. And that's how it was set up. What's different about this is we are not connecting to a ground that is a ground all the time. Our VCC pin connects directly to power. The side that we will be doing pulse width modulation on is on the ground side. It is a low side driver. We will be pulse width modulating the ground pins for the R, G, and B pins. What that means when we talk about duty cycle, remember, duty cycle is the percentage of on time. We actually want to change the duty cycle based on the off time. The off time is the low signal, and the off time allows us to make that pin a ground. So for now, we'll just leave it at 50. It's exactly where it needs to be. It's because it's 50% on time and 50% off time, but we'll need to address that in a future program. The next set, we are changing the physical locations of the pin, and we are telling the GPIO that we want to use the physical locations of each of the pins. Next, we set up pin R to be an output. Even though we are making pin R a ground, keep in mind that that ground is still an output. The final item that we will be doing is turning off the LED. When we do GPIO.output, we change pin R to high. There is no potential or difference in voltage between the pin 11 and the voltage that we've connected it to. We will then pulse width modulate pin R. So we want to set up a pulse width modulated signal. We have to provide it two things. The first thing is the location of the pin. In this case, it will be pin 11. And the second thing we will be doing is setting the frequency. And our red signal frequency in this example is 2000. The next item that we will do is run a while loop. This while loop will always execute until we press Ctrl+C. And we are pulse width modulating our pin. So we take that pin that we've assigned, the variable PWN_R_pin, and it now has a method that is called start. Start allows us to pass a duty cycle to an output, and then that output then produces a pulse width modulated digital signal. What we have to pass to it, we've already told it the frequency and location. What we have to pass to it is the duty cycle. Here we've set the variable red signal duty cycle to 50. And so we are passing the pin 11. We're telling it to start the digital signal at a duty cycle of 50. When we press Ctrl+C, we would exit out of that while loop, print end of program, and then we run a GPIO.cleanup. Alright, so that's the code. Let's go back to our terminal, and we will be running this code. So I can exit out if I've made any changes. I haven't made any changes. When I exit out of there, we can see that we are back in our terminal and that we've ended that call to Thony. I'm going to hit the clear here, and then we will proceed with running the code. All right, in the terminal, a good practice is let's take a look at the files that are in Lab4. So if I issue an ls command, the ls command will show me the files that are available. The next thing that I'll do is run the Python script. So I'll type the word Python space and then Lab4.1. And then if I hit tab, I can get a .0.py, and that will begin executing my Python script. When I execute the Python script, I should see my LED illuminate. It will illuminate the color of red because we are grounding the R pin. We should see also that it is only half of the normal brightness because we're running it at a 50% duty cycle. Connect a multimeter to your breakout board so that you can see the change in voltage that we have occurring on the pin number 11. In order to do this, we will take our red multimeter lead and connect it to the 3.3 volt power source at pin number 1. And then we will take our black meter lead and connect it to the physical pin number 11. This will allow us to read the voltage of the circuit. If your meter doesn't have the leads that can go into the breakout board, I would recommend taking a jumper wire and connecting it to the breakout board, and then put your meter leads on the other end, the male terminal of the jumper wire. Press Ctrl+C to exit out of the script. Notice that when I exit the script, my voltage, rather than going to 0 as I would expect it to, it has gone to 3.162. We can also see that in the terminal, we are running a keyboard interrupt, and at no point do we see an end of program statement like we were supposed to print when we ended it. So right now we are in a we have a problem with our script in that it does not correctly clean up at the end. Let's take a look at what we need to do in order to clean up this script.